So now we get to approach an interesting topic. It's internal forces. And you'll see what's meant by that as we go. But basically what we're interested in is if there is force inside of the material, can we determine it? Because if you think about it, a beam or a body or any type that has loads on it, those loads are transmitted from one of the end of the body to the other or to multiple points within the body. So what if we imagine a section or a portion, a free body of just half of that body? Well, there must be forces in the material, and that those forces are very important for later classes when you're going to learn about stress analysis, in particular in strength of materials. Now, it's very closely related to what we've already done with trusses. In fact, we call it the method of sections in order to determine loading inside of material in two-dimensional loading cases. So by the time we're done with these slides, you should understand more about how to accomplish this and why it would be important. There are many other bits of information in the slides. Be sure you look at them on the course website. Go through the example problems, group solving problems, etc., since we are not in class today. What applications are there of this? Well, we learned a little bit about beams. Rather than two force members, beams are components that have some lateral load. They have something that causes bending. Think about a pencil or a ruler or something, okay? So you've got a load in the center that's transverse or lateral would cause bending of the particular member. And so the loading is a little more complicated than a truss member that is just, made up of two force members. So in this case, we've got a beam that is spanning two columns. You notice there's less material in the center. That may or may not be a good idea. At the center of the span, there's less material, but it definitely supports a lateral load because the weight of the vehicles passing over this, or cars, or whatever the case may be, bicycles, people walking, I don't know. It looks like a roadway. That weight is certainly oriented at 90 degrees to the length of the beam. And so the beam has to support that load. It's not a simple member that has just, two forces, and so they're just collinear. So we're really interested in how the loading inside of the beam varies, because think about it. How would you know how big to make the beam? This one's tapered. Is it a good idea or bad? You might have the idea that if you find an area of the body where there is less load, you're going to need less material, and you would be right about that assessment. So understanding how the load inside of a body varies as you move through various positions within the body, in particular beams, is particularly interesting and useful to us. Here's an example where a billboard sign is supported by a column. Now, you'll notice that the column has to support not only the weight of the billboard, but the billboard is sort of cantilevered off, so there's a moment, certainly, in the material. And, of course, if there's a huge wind load, we can't afford for this thing to just fall over. And so you notice that the column that supports this billboard is actually larger at the bottom than at the top. Now, your intuition probably understands that and says, yeah, it seems like that there's going to be a higher load at the bottom. But how would you calculate the magnitude of that load? How do you know how much load there is? Well, that's what we're going to learn. Here's one last example where there's a shop crane, and notice reinforcement has been added around the top. Rather than just relying on the weld where the piece of pipe has been cut at an angle and welded together, there's actually a fairly small addition at the top, and it's certainly not as large as the pipe. Now, that pipe is probably hollow, but still, it seems strange that there's such a small amount of material, but the key is that it's far away from the other. And also it's on the correct side. Because if you think about it, what's going to happen is, well, if I can represent it with my hands, there's an upright portion and a cantilevered portion. It's going to try to fall, right? As you put a load on it, it's going to try to bend. So that extra material at the top, what it does is it is in tension, and so helps to support the structure so that it doesn't deform excessively. So that's why this was done. All right, so internal forces. So let's just take a simple example where we have a beam simply supported, so it's pivoted on the right, it's a roller connection on the left, and there's a lateral load of 6 kilonewtons and a moment load at D of 9 kilonewton meters. And we want to make sure that this beam can support these loads. I mean, think about it. If you make this beam out of paper and it's only a quarter of an inch tall, it's not going to support these loads. You probably have enough intuition to know that. On the other hand, do we need a beam that's 3 foot depth and this is 9 meters long, so you could fit it, but do you need a beam that has that large of a cross section to support these loads? Well, we better figure out what the loads are. So usually what you'll do first is you'll go ahead and calculate the support reactions. We've been calculating supports for quite a while, but a lot of times that will help quite a bit. In fact, in this case, if we wanted to know the load at B, for example, at section B, just underneath that point load of 6 kilonewtons, we would need the reactions at either A or D in order to calculate the properties or the forces at the cross section at B. Then what we do, here's the key. Then what we do is we imagine one section of the body to be separate from the other, because think about it, if the beam is all together, it's sort of holding hands there. Well, what sort of forces are in the beam? It's whatever's required, whatever force one half of the beam is putting on the other and vice versa from the other piece. Those are the internal forces we are interested in. And so we think of these as free bodies, because if you think about it, whatever loads we calculate there must be applied at that point in order to keep that body from coming apart. And of course, the way it does is because the material is all just homogeneous; it's all just connected together internally. But we can still talk about the loads required on this free body in order to maintain equilibrium. That's how we're going to calculate the internal loads. So we use the equations of equilibrium to simply solve for these loads. Now, there are only 3 loads to be concerned with because we're in 2 dimensions. There's a horizontal force, a vertical force, and a moment out of the plane. Those are the only 3 forces that are possible. This is a very powerful method. It's very useful, and it's a good idea and very insightful. So we're going to use it. Now, in 2-dimensional cases, the 3 unknowns, the 3 loads within the material that we care about are a shear force, a bending force, a bending moment, and a normal force. Now, they're always in the same orientation, okay? So the shear load is always acting along the cut face. It's always, in the case of a beam, it's almost always vertical, as you see here. But wherever the face is cut, the shear force acts along that cut face. It's parallel to the cut then. And we're not going to do anything odd like make a cut at an angle. We'll do that in strength of materials. There's a reason for thinking about that, but right now we're not interested in that. We're just taking a plain, simple cut so that we end up with fairly straightforward internal loads to deal with. So then there's the normal force, and that's axial. That's along the length of a beam, for example. But this would work for any shaped body. And then finally there's the bending moment. And a lot of students struggle to understand the bending moment within the material, but you can think of it this way. We've got 2 parts of a beam, and they're connected together, obviously, in the real world. We're thinking of them as being separate. If you struggle to understand the moment within the beam, think of putting a motor to connect the 2. So the motor shaft connects to one part of the beam, and the body of the motor connects to the other. And however much torque the motor has to apply, that's the moment within the beam. That's actually how much moment one part of the beam applies to the other, and the other applies to the original. They have equal and opposite. As a matter of fact, all of these loads, all 3 of these loads, the moment and the 2 forces, are equal and opposite on the 2 sides of the free body where we've imagined a cut. So that's really important to remember. Another thing that's important when we start drawing shear and moment diagrams, which will actually be calculating or determining the loads throughout the entire length of the beam. When we do that, there is a sign convention. You may as well go ahead and get used to it now. Notice we've got a beam here. It's really common. The left-hand free body diagram is a right-hand cut face. Okay, so it's at the right end of the beam, where, I shouldn't say the end of the beam, it's at the right side of the cut. That's not how I want to say it either, but you see it there with the shear pointed downward, V sub B pointed downward. We take shear downward on a right-hand cut face to be positive, and a moment counterclockwise to be positive. However, if the cut face is a left-hand cut face, then we take shear up and moment clockwise to be positive. It's a sign convention that has really nothing to do with a typical XY coordinate system. It's simply useful when we get to shear and moment diagrams, and it'll match the typical coordinate system very well. So we'll see more of that when we get to shear and moment diagrams. But just for now, to get used to seeing a right-hand cut face having shear force pointed downward and moment counterclockwise, and opposite then for the other cut face. Of course, the normal force we write like a tensile force, and of course, any of these can become negative, right? We could calculate these loads and find, oh, we assume the wrong direction, and so this is a negative load within the material. But we'll see how all of that goes a little later. But the net force within the body has to be 0, and so these are all equal and opposite to one another. So how do we determine all these internal forces? Well, we decide where we want to cut the body. So imagine a cut wherever we need to determine the forces. And then after that, it's really wise to figure out which side of the body that remains is best to analyze. Because in the example I just gave you, there was a moment applied over on the right-hand side free body, whereas on the left-hand side, we just had a reaction. You might say, well, it seems like that moment that's externally applied would affect the left-hand side body. It does, you're right. However, notice that that moment would come into play when we determine the reaction at A, at that support. And so the effect of the moment is sort of already baked into the reaction, okay? So you don't have to worry about, well, I feel like I'm throwing away half the body and there's something important there that's going to affect this other piece. You've already taken it into account once you've got the reactions. So decide whichever side's easier to analyze. It doesn't matter. You'll get the same result, just equal and opposite. If you need to determine the support reactions, now most of the time you will need to determine the support reactions for the entire structure. In fact, I would say probably it's best to set this as step 1, because most of the time it seems like you can't get away without calculating the reactions. So it's good practice. I'd recommend you just calculate the reactions from an overall free body diagram. That way you're not confused between that free body diagram and the free body diagram where you've cut it and you've discarded a portion of the body and kept the remaining for analysis. Then draw a free body diagram of the piece that you still got, and remember to show all 3 of the loads, the normal load coming out, the shear, and the moment, and show those at the cut surface. And then finally, apply the equations of equilibrium to that free body diagram and solve for the unknown internal loads. Because think about it, you've got 3 equations of equilibrium, so you can accomplish, or you can accommodate, 3 unknowns. So it works out nicely.